All right, today we're going to unravel a performance mystery that honestly, it kind of breaks a core rule of computing. It's a story about a critical app, a very frustrated team, and a fix that, well, it broke everything even more.
So this is the big question, right? It's the whole reason we're here. We're always told, more memory is better. It fixes crashes, it makes things faster. But what happens when the very thing you do to fix your app is what grinds it to a complete halt? Let's dig into how that is even possible. So, let's set the scene. Our story kicks off with a real-world, hair-on-fire production crisis. You've got a team battling this bizarre issue that seems to defy all logic. All their debugging, everything.
Okay, so the application we're talking about is a high-speed data aggregator for IoT devices. You should think of it as the central nervous system for monitoring really important industrial equipment. So latency here, it's not just a nice-to-have performance metric. It is a critical business requirement. That data has to flow, and it has to flow smoothly.
But it's not flowing smoothly. Not at all. Every few minutes, the entire service just stops. The data stream freezes solid for up to 2 seconds. And then, poof, just as suddenly it comes back to life like nothing ever happened. These stop-the-world pauses are causing absolute chaos for everything that depends on this data.
So the team, they do what any of us would do. They look at the metrics. Memory usage is high, but it doesn't look like a leak. They see that classic sawtooth pattern, which usually means memory is being used and then, cleaned up properly. So they make a logical guess. The process must be getting starved for memory. The solution seems obvious. Just throw more resources at it. So they double the container's memory limit to 4 gigs.
And this is where the story gets really weird. Adding more memory didn't just fail to fix the problem, it made it catastrophically worse. The pauses didn't just happen more often, they got way, way longer. We're talking those half-second hiccups ballooning into 3, even 4-second freezes. The application was now completely unusable. So how? How is that even possible?
Okay, to solve this mystery, you have to take your simplest idea of how memory works and just throw it out the window. The team's biggest mistake was thinking of memory as one giant container for stuff. The reality, especially in V8, which is the JavaScript engine behind Node.js, is way more complex.
So on the left, you see the flawed model the team was using. Memory is one big bucket you just fill up. But the reality is over there on the right. V8 doesn't see one bucket. It sees at least 2 very different spaces, and it treats objects completely differently based on how long they've been alive. And that distinction, well, it's the key to this whole mess.
So, the crucial takeaway here is this. The problem was never a memory leak. The objects were getting cleaned up. The real issue was the process of that cleanup. It was all about where these objects were living and the ridiculously high cost of evicting them from the wrong memory neighborhood.
All right, let's pull back the curtain on V8's memory manager. You probably know it as the garbage collector. Think of it as the silent janitor of your application. And trust me, understanding its strategy is the only way we're going to solve this mystery.
You know, V8's entire memory strategy is built on this one simple, powerful observation about programming. It's called the generational hypothesis, and it basically says this. Most objects your program creates are used for a tiny amount of time and then they're immediately useless. V8 is absolutely, obsessively optimized around this one single fact.
And here's exactly how V8 uses that hypothesis. Think of your memories being split into 2 main areas. You've got new space, that's your workbench. It's small, it's messy, and stuff is constantly moving on and off it. Cleaning this space is incredibly fast. Then you have old space. That's the long-term warehouse. It's huge, and cleaning it out, what we call a major GC, is a slow, expensive operation that stops your entire application. And here's the kicker. The bigger that warehouse gets, the longer it takes to clean. You see the connection to our mystery now?
So, let's trace the path of a disastrous object. First, it gets created on the fast workbench, new space. But if it's still needed after a couple of those super fast cleanups, V8 makes an assumption. It thinks, hey, this thing seems important, it's sticking around. So it promotes the object. It moves it from the workbench all the way over to the deep storage warehouse, old space. And that single decision just set a ticking time bomb.
And it turns out the data buffers in that IoT app were the absolute perfect storm for this system. They didn't die immediately, so they always survived the fast cleanups on the workbench. But they also weren't meant to live forever. They were these medium-lived objects, basically temporary items that were mistakenly being shipped to the long-term warehouse where they just clogged up the whole system. So now that we actually understand the disease, we can talk about the cure. And it's not about tweaking some memory flags. It's about fundamentally changing how we design our applications, keeping a concept called allocation pressure in mind.
The real key is learning to spot these medium-lived troublemaker objects. The ones that live for just a few seconds. They're too old to be quickly cleaned up on the workbench, but they're nowhere near old enough to justify a permanent spot in the warehouse. They live in this awkward gray area that V8's optimizations are just not built to handle.
So what could the team have done differently? Well, they had better options. They could have moved those buffers to an external store, like Redis. That keeps the app's memory footprint super tiny, but you pay a price in network latency. Or for the absolute best performance, they could use something called off-heap storage, where you manage memory yourself. This completely bypasses the garbage collector, but it brings in a ton of complexity and risk. As they say, there's no free lunch. It's always about trade-offs. So this gives us the right way to think about it. Your application's memory should be a river, not a reservoir. Data should flow in, get processed on that workbench of new space, and then just disappear. The warehouse of old space should only be for the permanent fixtures of your app, your code, your configuration, the stuff that's truly meant to live forever.
Okay, let's just zoom out for a second. This isn't just some abstract technical puzzle. These garbage collection pauses, they have real, tangible costs to the business.
What's really shocking is how much of your CPU time can be secretly stolen by the garbage collector. It's not running your business logic, it's just cleaning house. In a poorly designed app, this hidden cost can actually become the main workload, starving your actual features of the processing time they desperately need. And that has a direct impact on the promises you make to your customers. You simply cannot guarantee a service-level agreement, an SLA, of, say, 50 millisecond response times if your application randomly decides to take a 2-second vacation every few minutes. The math just doesn't work. So what's the big takeaway here? Don't just watch memory usage. You've got to look deeper. Start monitoring the duration of your different GC events. Track your promotion rate, how many megabytes per second are getting moved from the workbench to the warehouse. And keep a close eye on the total percentage of time your app spends just on garbage collection. These are the true vital signs of a healthy memory architecture. And that leaves us with one final, and I think crucial question you should ask about your own applications. Are you treating memory like a river where data just flows through and vanishes? Or have you accidentally built a dam where temporary data gets stuck, just waiting to cause a catastrophic flood in the form of a long garbage collection pause? The answer could be the key to your next big performance win.